Right. So we know that nuclei whose binding energy per nucleon is less than 8 mega electron volts are found to be unstable in nature. Okay. Now, those nuclei having mass number more than 170, fine, they all have binding energy per nucleon less than 8. They are unstable. So basically, these nuclei are too large to be stable. So what they do is they break down into smaller fragments. They undergo fission reactions. We had discussed that in the last class. Now we also see that nuclei with mass number less than 30 are unstable. All these have binding energy per nucleon less than 8 mega electron volts. Fine. Basically, these are too small to be stable. So what these nuclei tend to undergo is fusion reactions. Two very light nuclei can combine to become a slightly heavier nucleus. And the heavier they become, the more stable they are. Okay, up to Fe56. Fe56 is the most stable nucleus. Okay. So lighter nuclei tend to undergo fusion reactions. One example of a fusion reaction is this fusion between protons. Okay, 1H1 refers to a proton basically. Okay, the nucleus of hydrogen. Nucleus of hydrogen only has a proton. The proton itself is the nucleus. So proton combining, they form 1H2. Then 1H2 combine to form helium. And 1H2 can also combine to form 1H3. These are the different possibilities basically. But these are examples of nuclear fusion reactions. You don't have to remember any of these, but just understand what happens in fusion reactions. Now, fusing means what? Combining. Two nuclei have to combine. Now, basically, what does a nucleus have? Protons and maybe neutrons. Hydrogen nucleus has only proton. Other nuclei, they have neutrons as well. Okay. Now, whether it's only protons or protons plus neutrons, the charge of a nucleus is positive. Consider this, for example, one proton and one proton combining. Now, proton is a positively charged particle. So, suppose there's one proton here, one proton here. Both of them have charge plus E and plus E. They have their own mass also. We know the mass of a proton. Now, if you want two protons to fuse, okay, see, they are positively charged particles. How will they fuse and become one? Electrostatic repulsion will be preventing them from coming towards each other or coming closer to each other. There will be electrostatic force acting outwards like this. But if they can somehow overcome that force, means if they have sufficient energy to overcome that force and come close enough, okay, how close? So close that the nuclear force starts to dominate. When does nuclear force start dominating? When the distance between the particles is approximately 1 Fermi or femtometer, that is 10 to the power of minus 15 meters. When they come that close to each other, the nuclear force will take over and then they will get combined into one nucleus. Fine. Basically, this is why fusion reactions are difficult. Okay, and they are very hard to be carried out in a laboratory setup. Fine, because for two charged particles to come that close to each other, a lot of energy will be needed. Let us do some basic calculation first. Try to solve this problem. Consider two protons. Okay, the magnitude of charge on a proton is approximately 1.6 into 10 power minus 19 coulombs. Let's say they are initially very far away. So initial separation between them tends to infinity. Okay. Final separation between them has to be approximately 10 power minus 15 meters. Right? Now you know how to find out potential energy between two charges. When they are at infinite separation, you find out potential energy. Okay, it'll be 10, it'll be zero anyway. Okay, need not find out. Tends to zero. Find out how much is the final potential energy. Okay, you can use calculator if you want. So if you can find out how much potential energy is needed, now see that potential energy, like when they come that close to each other, some amount of potential energy should be there. This potential energy has to be initially in the form of kinetic energy. We have to give that kinetic energy to the protons so that as they come closer, 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 they lose that kinetic energy and it gets converted to potential energy. So basically, this is the idea. One proton and another proton should be projected towards each other with sufficient amount of kinetic energy such that they come close enough, they come to a distance of 10 power minus 15 meters from each other. By then, they can lose all that kinetic energy. So, whatever is the initial kinetic energy the protons had gets converted to final potential energy. Right. So, use the formula for potential energy between point charges and calculate what is the potential energy of two protons when they are at a separation of 10 power minus 15 meters. Do this quickly. One of you quickly tell me what is the formula for potential energy between point charges? We use this in the last chapter also, atoms, to find out the closest distance of approach between an alpha particle and the gold nucleus. Okay, anyway, it is K Q1 Q2 divided by the distance between the charges. K is 9 into 10 power 9 approximately. Q1 Q2 charge of protons 1.6 into 10 power minus 19. You square it. It becomes 2.56 into 10 power minus 38 divided by what distance do we want them to come to? 10 power minus 15 meters. Okay. So this answer will be in joules. So the energy required will be 9 into 2.56 is approximately 23, and 10 power 9, 10 power minus 38 will be 10 power minus 29, another 10 power 15, so 10 power minus 14. So you can write this as 2.3 into 10 power minus 13 joules. Fine. It's a very small amount of energy considering just one proton and one proton. But if you want a large number of protons to undergo this reaction, large number of protons in the sense, let's say 1 gram of hydrogen you want to fuse. 1 gram of hydrogen has 1 gram of hydrogen means 1 mole of hydrogen, right? Because the atomic mass of hydrogen is 1 gram per mole. 1 mole is how many atoms? 6.023 into 10 power 23 atoms. If those many nuclei fuse, then you will need this energy multiplied with that number, multiplied with 6 into 10 power 23. Then it becomes a large amount of energy. Okay. But see, this potential energy also, this is the potential energy or the energy we need to supply for two protons to fuse. Fine. And there's also, and it also, it's not guaranteed that if you give this much energy, they will definitely fuse. For them to fuse, okay, accidentally, they should be moving exactly towards each other. Okay, you can't hold a proton and make it exactly move towards another proton. It should happen by chance only. Fine. So if you just put two protons in a container and give them this energy, there's no guarantee that they will fuse. They will have that energy, but they'll be moving in random direction also. Why will they move exactly towards each other? So if there is a huge collection of protons, like many moles of protons, and you supply enough energy, then there is a chance that some of the protons may move exactly towards each other and fuse. Okay. So you will have to supply a lot of energy for this reaction to be actually carried out. So even if it is just two protons, they need to have this energy in the form of kinetic energy initially. Okay. Now proton basically is a single particle. You can treat it as a monoatomic gas. Fine. For monoatomic gas, the kinetic energy, okay, you must have learned this in thermodynamics actually, kinetic energy per molecule of a monoatomic gas is given by 3 by 2 kb into T, where kb is Boltzmann constant. Okay, this is from Maxwell's law of equipartition of energy. Monoatomic particles or monoatomic gases have 3 degrees of freedom. What Maxwell's law of equipartition of energy states is each degree of freedom gives an energy of half kT to the molecule. So if there are 3 degrees of freedom, the molecule will get an energy of 3 by 2 kT. It can store that much energy. Okay, where K is Boltzmann constant. Now, how much is Boltzmann constant? Just a moment. Exact value. 1.38 into 10 power minus 23. Okay. So kinetic energy per molecule as a function of temperature, you can say it is 3 by 2 into 1.38 into 10 power minus 23 multiplied with the temperature T. Now, this is the formula for kinetic energy per molecule. In monoatomic gas, atom itself is the molecule, right? So you can say per atom, this is the kinetic energy. Now, how much energy is needed for two protons to fuse? This much. So you can equate this to 2.3 into 10 power minus 13 and estimate the temperature to which the protons will have to be heated in order to make this fusion reaction happen. Now there's a 10 power minus 13 on the right side. There's a 10 power minus 23 on the left side. You send it this side, it becomes 10 power plus 23. 10 power minus 13, 10 power 23 is approximately 10 power 10. And some other numbers are also there. You adjust them. You will see that the temperature will have to be approximately 10 power 9 Kelvin. Okay. For two protons to have sufficient energy to fuse. This is why it is very difficult to carry out fusion reactions in the lab. Okay. Basically, we don't have materials which can withstand this much temperature. Fine. But in stars, this is what happens. Stars have sufficiently high temperature to make protons fuse. Okay. So proton, 1H1, 1H1, when they fuse, they can form 1H2 and later they can form helium. Okay. So basically in the sun, this is what happens. Hydrogen or protons fusing to form helium. Now, what if all protons in the sun fuse to become helium? Then helium will start fusing. Okay, helium fusing. There is a separate chain step. There is a separate sequence of reactions in which they form carbon. Okay, so if all the hydrogen in the star is exhausted, it gets converted to helium. Then helium nuclei will start fusing. They will convert to carbon. Okay. Carbon's mass number is also just 12. It's still unstable. Carbon can also fuse and then finally stability will be attained. So basically look at the binding energy graph. Protons 1H1 has a mass number 1. Okay. If they fuse and become helium, okay, 2He3, let's say they become 2He3. From mass number 1, it is shifting to mass number 3. From mass number 1, if it goes to mass number 3, basically binding energy per nucleon is increasing. Again, helium, if they combine and fuse to become carbon, carbon is C12. So mass number increases, its binding energy per nucleon increases further, but it still does not touch 8. Okay, it does not become 8. So C12 is also unstable only. Okay, almost stable but slightly unstable. C12 also can combine and form a sufficiently bigger nucleus. Okay, a sufficiently heavier nucleus which whose binding energy per nucleon is more than 8. Okay, so suppose all the hydrogen in a star is exhausted, it will be in the form of helium. All the helium is exhausted, it will be in the form of carbon. All the carbon is exhausted, then it will be in the form of a stable nucleus. That is when fusion stops. Okay, when carbon nuclei fuse to become a heavier nucleus, obviously that heavier nucleus which is formed will have a binding energy per nucleon more than 8. It will be stable. That is when the star is said to be dead. Okay, it cannot release energy any further. Only as long as these fusion reactions are happening, it will be able to release that energy. Okay. So basically fusion is difficult because nuclei which are positively charged have to come within a distance of 10 power minus 15 meters of each other. For that, we have to supply a lot of energy. So the gas or the, what do you call, nuclei will have to be raised to temperatures as high as 10 power 9 Kelvin, which is difficult to do in the lab. But scientists are developing materials which can withstand this temperature. And as I said in the last class also, very recently, fusion reactions have successfully been carried out in labs also. Okay. So it's called controlled thermonuclear fusion. Fine. So in a laboratory setup, you can make nuclei fuse. Okay. It is now possible. It's not widely available, but it has been made possible. Okay. Fine. That is all there is in this chapter. We talked about properties of nuclei first, mass number, atomic number, then what is mass defect. Okay. Free nucleons have more mass compared to nucleons when they are inside the nucleus. And free nucleons have more energy compared to energy inside the nucleus. So there's a relation between energy and mass. E is equal to mc square. Then we talked about size of a nucleus. Okay. Radius r is equal to r naught into a power 1 by 3, where r naught is 1.2 into 10 power minus 15 meters. So it is proportional to mass number to the power 1 by 3. When you find out the volume, you'll see that volume is proportional to mass number. Then you calculate density, you'll see that density of all nuclei is almost the same, whatever be the mass number of the nucleus. Then we talked about binding energy of a nucleus. It depends on mass defect. Okay. Binding energy is mass defect multiplied with c square. So binding energy is the energy that we need to supply to free all the nucleons from the nucleus. Right? And the stability of a nucleus depends on binding energy per nucleon. Okay, so binding energy divided by the mass number. And if this is greater than or equal to 8 mega electron volts, the nucleus is found to be stable. And to do calculations based on mass and speed, if masses are given in atomic mass units, remember, one atomic mass unit corresponds to an energy of 931.5 mega electron volts. Usually they'll give you this in the question, but it's not given also. Like if you solve a few problems, you will remember this value anyway. Okay. Then we talked about stability of a nucleus and nuclear reactions. Fission reactions in which a heavy nucleus splits into smaller nuclei, releases energy in that process. Based on their binding energy per nucleon and their mass numbers, we can tell how much energy is released. Those are the kind of questions we solved in the last class. And today we discussed about fusion reactions. Okay.